2.3 Continuity Part 1. Your objective for this lesson is to identify continuous functions. Okay, so the definition of a continuous function is a function whose outputs vary continuously with the inputs and do not jump from one value to another without taking on values in between. Basically, you want to be able to draw a graph without lifting up your pencil at all. So no lifting up the pencil. And this concept is related to what we were just studying with limits, and it is also related to topics that we will look at in the near future. So this is a very important concept. Example 1, find the points at which the function f is continuous and the points at which f is discontinuous. So I can just look at this graph and you can see that you would not be able to draw this without lifting your pencil. There's multiple parts and it just would not be possible. So the entire thing is definitely not continuous. If I wanted to test this, I could put my pencil down here, draw, and I have to lift my pencil. So it is not continuous or discontinuous. Discontinuous at x equals 1. Okay, so let's start up again. Up, and I have to move up here. So x equals 2. And for the rest of the graph, we're okay. So these are the points at which it's discontinuous, and it is continuous at all other points, basically. So at all other points in the domain which is 0 to 4 inclusive. So square brackets mean inclusive. And you'll notice that the points at which this graph is discontinuous are the points where the two-sided limit either does not exist or where the function is not equal to the two-sided limit. So if I took the right and left hand limits of x approaching 1, so right hand limit of f of x, right hand limits are going this way, we get 1. And the left hand limit coming this way, that is 0. So 1 and 0 are two different numbers, so it's discontinuous there. So when the limit, right and left hand limit aren't equal, you have a discontinuous function. And here, if we're looking at, well, the right hand and left hand limit of 2 are the same. You can see they're going to the same point. But if you look at the limit of as you're approaching 2 of f of x, you get 2 as opposed to f of 2, which is, oh, sorry, this isn't 2, this is a 1. So this limit is 1, but the function is 2. So those aren't equal. It's discontinuous at that point. This is opposed to, let's look at the limit as x approaches 3 of f of x. You get, this is 3, we get a 2, and f of 3 also equals 2. So when these 2 points match, or not points, when these two numbers match, the point is continuous. The function is continuous at that point. Okay, cover some of this up. Continuity of a point. So there are two types of continuity at a point. There is one-sided continuity and two-sided continuity. We're going to look at two-sided continuity first. So you can see for an interior point that's at the the interior of a graph. I'll show you a picture in a minute. A function y equals f of x is continuous at an interior point C of its domain if the limit as x approaches C of f of x is equal to f of C. So this is what we just went over. If the limit at a point is equal to the function when you evaluate it at that point, then it's continuous. The function's continuous at that point. And for exterior points, a function y equals f of x is continuous at a left endpoint, A, or continuous at a right endpoint, B, of its domain, if the right-hand limit of A is equal to f of A, or the left-hand limit as you're approaching B of f of x is equal to f of B. So let's look at our graph. Okay, so this is the graph of that, and you can see here this at point C, we're talking about our two-sided continuity, the interior point here. So you can approach C from both the right and the left to find the two-sided limit. When the two-sided limit is equal to the point on the graph, then it's continuous at that point. And for the exterior points, when that single-handed limit of either end of the graph is equal to the point on the line, then you have a continuous function. Okay. So if f is not continuous at point C, we say f is discontinuous. So dis is not discontinuous, not continuous at C, and C is a point of discontinuity at f. And please note that C does not have to be in the domain for this to happen. So obviously, if the function is not defined at a point, then it is discontinuous at that point. Okay. Example 2. Find the points of continuity and the points of discontinuity of the greatest integer function. So this is a graph of the greatest integer function. This would be in your book. They write y equals int x. You'll see me write it this way also. And it is your step function here. So for a function to be continuous at x equals c, and that would be like x equals 2, x equals 3, the limit as x approaches c must exist. So the limit must exist, and it must equal the value of the function at x equals c. So continuous, we're going to check for does the limit exist, and is the limit equal to f of x. Okay. Okay. And you can see here, remember, if you're looking for the easy definition of continuous, it's that you're not lifting up your pencil point as you draw this graph. If I were to try to do that, I would have to pick up my pencil every single time I hit a new integer on this graph. So this graph is discontinuous at every integer. And if we were to use this definition here, you could take the right and left-hand limit of each integer. So if we were to do 1, so the limit as we approach 1 from the right of int x. So approaching from the right, we get 2. And then the limit as we approach from the left of int x, we get, gosh, why did I write 2? This is a 1. We get 0 here. So 0 and 1, 2 different numbers. So since these limits, the right and left hand limit, are different values, the limit does not exist. So the limit does not exist, and therefore the graph is discontinuous. So discontinuous at x equals 1. And it's going to be the same story for every integer. So at 0, 1, 2, 3, 4, 500, same idea. So what I'm going to conclude here is that the greatest integer function is discontinuous for any integer x. Your book puts this a little bit differently. If you want to go look at how they worded it, it's on page 75. It is continuous at every other real number. Okay, this would be my answer here. Okay, so let's look at types of discontinuity, and I believe this is the last part of this video. So types of discontinuity you can see again on page 76 in your book. The first graph I have here is just a simple linear function, so y equals f of x. And you see that I could trace this pretty easily without picking up the pen. There's no holes, no jumps. It's just a nice clean graph. So this is continuous at every point, but we're going to look especially at x equals 0. Notice that there is not a hole there. Next, I'm going to compare this to removable discontinuities. They are called removable discontinuities because you could take them out pretty simply. All you have to do is, for these two, set f of 0 equal to the limit. You could fill in the holes. So this one here, it is just a hole. There isn't another value. And it would be continuous if I just plugged in that hole at f of 0. So if I put a point at f of 0, put it in at 1, that would be a continuous graph. But there is no point there, so it's discontinuous. Okay. Next we have this other graph also with a hole in it, and it has a point at 2, or not 2, at 0, 2. So this is an issue because to be continuous, we would need the point at 0, 1. So if we could move that down, then the graph will be continuous, but we can't really do that. So it is a discontinuous function. So both of these are discontinuous, but they are both removable because the discontinuity is a hole. So holes are removable discontinuities. Okay, the jump discontinuity. This is called a jump because the graph was down here and now it's up here. It jumped up. You could jump down. This is not removable. It's not really easy to just plug that in, but this is a jump discontinuity. So the one-sided limits both exist, but they are different values. So therefore, if I tried to take the limit as x approaches 0 of this graph, this does not exist because the two one-sided limits are different values. Okay, and infinite discontinuity. So the limit here also does not exist because you're going up towards infinity. There is no limit. Yeah, there's a vertical asymptote right here. So you can't get rid of that. And we have the oscillating discontinuity. So this one is just all over the place. It isn't necessarily approaching anything, but it's just bouncing back and forth. So yeah, this oscillates too much to have a limit as x approaches 0. Oscillates too much to have a limit as x approaches 0. Okay, and an example of this would be y equals sine of 1 over x. Okay, so those are your basic discontinuous functions.